Welcome back to the Puddin' Creek Rod Shop. Now what you're looking at is my 1932 Ford sedan with a hot little Buick nailhead engine in it. But that's not the project we're working on today. Today we are working on another 1932 Ford, a chopped and channeled Survivor show car, a car that was featured in the 1976 issue of Hot Rod Show World, a car called the Bad Coupe. Now today is a day I've been looking forward to ever since I tore this car apart. Today is a day we start the restoration process on these super cool old chrome hairpins. Now these are greasy and rusty and crusty, but we're going to restore them and make them shine like a diamond. Now when I took these off the car, I didn't do anything to them. I didn't degrease them. I didn't check the ball joints. I didn't do anything but hang them on this nail so they wouldn't get torn up. Googly moogly, would you look at the rust on them threads? Well, on the chrome plating too, but especially on the threads. Can you imagine trying to dial in the front end geometry on this car with those threads rusted up like that? We better get these threads soaking in some deep creep. Now some of you guys have messaged me and asked me, "Hey Puddin' Creek, why is all the chrome on the Bad Coupe so rusty?" Well, we pulled this car out of a museum in Mentor, Ohio, Don Moyer's Museum of Speed, and Don Moyer's Museum of Speed is located literally about a block from the shores of Lake Erie, so it's a pretty wet environment. Now, Don's building was not climate controlled. It was just a building like my building or your building. So I'm guessing all that humidity coming in off that lake was working right into the building and working on this chrome. Now, the Bad Coupe had sat in Don's museum for about 7 years, but I don't think that's where most of this rust came from. You see, before Don got a hold of the car, it's my understanding that this car sat in storage in a masonry block building for almost 40 years in Ohio, in Mentor, Ohio. So I'm guessing that's where all this corrosion came from. I have no idea what shape the ball joints are in. Like I say, I didn't check anything when I took it apart. And I'm assuming all that old grease, that 40, 50-year-old grease, is just hardened down in the ball joints, so I don't know that we can even tell by feeling them until we get them soaked and degreased and cleaned up. But let's see what they feel like right now. Well, honey hush, that feels pretty doggone good, even with the old crusty grease. I'm guessing if we cleaned them out real good and put fresh grease in them, these ball joints would be pretty good. That one don't feel bad. That one feels pretty decent. I believe we might be all right. I sure would like to save these old chrome made in USA ball joints if there's any way possible. Well, maybe I spoke too soon. This ball joint right here looks like Earnhardt put it in the wall in turn 3 at Darlington. But the actual ball feels great. It's just that retainer ring's got all mashed up somehow or another. I'm not sure what we'll do on this. First step will be get it out and get it degreased and cleaned up so we can see what we've got. Now off camera, I did a lot of work to these spring perches. The threads were really pretty bad messed up, but I took a rethreading die and I straightened them out, and they still look rough, but the nuts go on there as smooth as silk now. Also, the shanks were kind of beat up. I took a flat file and I smoothed down all the high places on the shanks and got them where they fit down in the bushings on the straight axle real good and smooth. Then I ran a reamer through these bronze bushings, and I took a countersink and countersunk both ends of the bushings to get rid of any high spots or bad spots. Then I took a piece of 9/16 rod and checked the fit on them, and they fit perfect. There was no wear or slop at all, so the bushings are in great shape. But when I tried the actual spring shackles in the bushings, they would go in, but they had a tight spot in them. So I done a little investigation, and I found out the old forge line on the outside of the shackle pin here, that had never been smoothed out, I guess, from the factory. So I took a stone and I stoned that out real smooth, and then I tried them in the bushings again, and then they fit perfect. So now I've taped off the chrome, and I'm going to shoot a little protective black paint on these shanks. Most of these shanks still have chrome plating on them, but at some of the places I had to file down the high spots, and that lost some of the chrome. And there's some rust pits that doesn't have chrome. So I'll shoot a little black on here just to keep them from rusting. And probably what will happen once we grease them up and put them back together in the axle, the final assembly, a lot of this paint will wear off, but it should stay down in the pits and the spots that don't have any chrome on them. All right, time to quit polishing and shining and get some real work done. Now this is the spindle that had the 10,000ths oversized kingpins in it, and you can see when they reamed this bushing out that they got rid of most of the grease valleys, and when they reamed the other side out, they even got down into the steel. There they went past the bronze and into the steel of the bushing. So that's not very good. This other spindle, that's the one that has the 859 thousandths Ford 70s Ford truck kingpin in it. And you can see when they reamed it, they lost all the bronze. That's just steel on steel. That's a steel bushing riding on a steel kingpin. That's not good. Let's see what the other side looks like. I'm assuming about the same. Yeah, just the same. No grease valley, no bronze, steel on steel. So that's no good. We'll address that later. The first thing we got to do is get these old bushings out. Now, the next step I'm about to take is probably totally unnecessary. I'm sure you're going to tell me that in the comments, and I'm going to agree with you. I don't think this is necessary either. But I'm going to make a spacer that goes between the two ears on the spindles, so when I go to press those bushings out, they won't flex or move or distort or do anything to hurt the spindles. I know those spindles are forged, and I know they're not going to deflect or move pushing a little brass bushing out. The only thing that keeps ringing in the back of my head is how hard it was to get those kingpins out that I've pressed a million out. There was no problem whatsoever. Things on this car seems to be really oversized, pressed in, and really corroded in place. Anyway, this will only take me 5 minutes, so for 5 wasted minutes, I'll knock out a real quick spacer, and I won't even have to consider whether anything's moving or flexing. Well, I was using a deep well socket to press this bushing out, and it was going pretty good, but I run out of room. My steering arm was going to hit the top of the press, so I've got the same deep well socket back in there again, and I'm going to put a little spacer on top and see if that won't finish the job out here. Well, there we go, a 1970s bronze kingpin bushing, or should I say bronze lined. These are actually a steel housing with a bronze lining inside, which was the problem. When they reamed these oversized, they got into the steel. What you want a steel kingpin with a bronze bushing so it slips and slides good. You never want the exact same material, steel on steel. You want dissimilar metals. So in other words, you want bronze and steel or brass and steel or whatever, but dissimilar metals. Now, I said you could use brass or bronze, either one, and that's true for a bushing, and I also have been calling these kingpin bushings, but technically these are kingpin bearings. Let me explain what I mean. A bushing is just something that takes up space. In other words, if you had a 1-inch hole and a 1/2-inch pin, you could put a bushing in there to take up that space. A bearing is something that two surfaces ride on, or a surface rides on. In other words, in this application, these are actually bronze bearings. Some people call them sleeve bearings or plain bearings. But these are bronze bearings because the kingpin is riding on the surface. This is a bearing surface. This is not just taking up space. And for a bearing surface, you want bronze and not brass. Now, I know what you're going to say. Puddin' Creek, I've heard those called kingpin bushings my whole life. Well, I have too, and I've probably called them that. But technically, this is a bearing surface, so this is a kingpin bearing, a plain bearing, or a sleeve bearing, a bronze sleeve bearing. You know, every once in a while in the comments, you guys write me up for calling an engine a motor. I'll say we're going to put the motor back in the bad coupe, and you'll say it's not a motor. Motors are electric. That's an engine, Puddin' Creek, and I know the difference. But where I was raised in East Tennessee, everybody called hot rod motors motors. So sometimes I say it right and sometimes I say it wrong. Anyway, engine and motor, the difference in that is kind of like the difference in bushing and bearing. It's not a big deal, but technically there is a difference. Anyway, bronze makes a much better bearing surface than brass, so if you're making something that actually is going to be used as a bearing, you want to use bronze. And since we're having engineering class today, here's a pop quiz for you. Do you know the difference in brass and bronze? Do you know what two materials it takes to make brass and what two materials it takes to make bronze? Put it in the comments if you know. All right, everybody got their guesses in the comments? Well, here's the answer. To make brass, you use copper and zinc. To make bronze, you use copper and tin. Now, there's a bunch of different alloys of brass and there's a bunch of different alloys of bronze, so there's other materials mixed in with those to get the different alloys, but the basic combination is copper and zinc makes brass and copper and tin makes bronze. Now, I know you're probably saying, Puddin' Creek, what's with the metallurgy course? I tuned in to see some hot rod work, maybe hear a little guitar picking or a funny joke, and now I'm getting a lecture on bronze and brass. Well, this is all going to be important because I have to put new bushings or bearings, whichever one you want to call them, back in these spindles. And if I put the bushings in that came with the kingpin kits, and then I ream them out for those oversized kingpins, I'm going to end up with the exact same result that they ended up with in the 1970s when they did that. I'm going to ream most of the bronze lining out and end up with steel on steel. So what we're going to have to do is make our own kingpin bushings. Now we're going to make our bushings out of solid bronze and just eliminate that outer steel sleeve altogether. So I did a little research to find out what kind of bronze, what alloy bronze kingpin bushings are made from, and turns out they're made out of SAE 660. Now SAE 660 is not anything weird. That's just standard what we always called bearing bronze in the machine shop industry. Now SAE 660 bronze is an excellent wear resistance and good load carrying bronze, and it has low friction because it has little pieces of lead embedded in it. fired up General Chow's bandsaw. I think what we'll do is just saw one blank right now and make up one kingpin bushing or bearing, whatever you want to call it, and do the process all the way through, press it in, check all the fits, make sure we got the whole thing figured out, and then make the other three to match it. Now, I've never actually made a set of kingpin bushings before, but I've made plenty of other bushings for hot rod parts, and I've made plenty of bronze bearings for industrial applications, so it shouldn't be too hard.
1, 2.
Now, before we make the bronze bearings, I need to fix some bad threads, the grease fitting threads, in the spindles. I've already tried my little clean out bolt trick, but that didn't work. I'm actually going to have to run a tap through these threads. Now, I don't want to run too big of a tap through the threads because I don't want to take a lot of material off. This tap right here is a GH3. Now, the letter G stands for ground, as in this tap is precision ground instead of just cut with a cutting tool. The H stands for high. That means the tap's pitch diameter is on the high side or oversize of the nominal pitch diameter. The number after the GH indicates how much oversized the tap is. So the bigger the number, the more oversized it is. And it's oversized in increments of half thousandths. So a GH3 grind would be 3 half thousandths oversized, or 1.5 thousandths oversized. For this application, I want the smallest GH number I can find because I don't want to take a lot of material out and make these threads sloppy or oversized. I just want to fix a bad thread. This GH2 tap is the smallest GH number I have, so it'll have to do. Now I'm using telescoping gauges to get a precision measurement on the bore diameter of these spindles. I'll need to know that so I'll know exactly what size to make the bronze bushing or bearing. And also I need to know that because I'm going to make a test shaft to run through these two bores and see if they are precision in line with one another. I assume they are, but I really have no way of knowing. So I put a piece of 12L14 in the lathe and I turned it down to 2 thousandths below the measurement I got with the telescoping gauges. So if these two bores and a spindle are perfectly in line, it should be a perfect slip fit on this shaft. If the two bores are not in line, there's no way in the world it'll go on this shaft. Well, good night, nurse. It's a snug fit, but it goes all the way on the shaft through both bores. I am continuously amazed at how good a quality Henry Ford was putting out in the 1930s and 40s. Here's the other spindle, same deal. With only 2 thousandths clearance, both bores line up perfectly. Now, the reason I wanted to know if those two bores were perfectly in line is because I would like to make my bronze bearings a lot closer tolerance than the ones that come in the kits. The ones that come in the kits are massively oversized on the outside diameter and massively oversized on the inside diameter. They are so much oversized it almost turns the whole operation into a blacksmith type job. Let me tell you what I mean. Most guys, when they get these big oversized bushings that come in these kits, they take a driver and a big giant hammer and they just have to beat the crap out of them to get them in. It's not really a precision type operation. It's more like watching a blacksmith make horseshoes. The outside diameter of these factory bushings are so much oversized that as you drive them in, they usually curl up a bunch of that steel that's on the outside. I mean, they are really oversized. Now, what I would like to do is to make my bearings or bushings a precision press fit so that they just press in smooth and clean. They're tight, super tight. They won't come out, but it's not rolling up a chip of the material on the outside diameter, and I sure don't want to have to beat them in with a sledgehammer. All right, I've got new inserts in my boring bar and my turning tool, and I've sharpened up my high-speed part-off tool or cut-off tool, whichever one you want to call it. Let's make some kingpin bearings. Alright, I've been checking the bore size just with a set of dial calipers just to get a general idea of where I'm at in the tolerance. And now I think I'm within a couple of thousandths, so let's take this homemade pin gauge that we made the other day and let's see exactly where we're at. Now what I'm shooting for is to make this a slip fit for the kingpin. The kingpin is 822 thousandths diameter. I want to get it where the kingpin just slips in, but not too big, just a precise slip fit on the lathe. Then when I press the bushing into the spindle, the kingpin probably will not fit, but I'll just have to lightly ream it out, ream a couple of thousandths out, and then it'll be perfect. Now I'm getting so close to my finished size that I'm going to start taking spring passes. Here's how a spring pass works. Say I dial the boring bar over 2 thousandths and make a pass through the part. I cut 2 thousandths out. Then before I measure it or check it, I'll back the boring bar out and just feed it back through again without dialing it over any. That's called a spring pass. That takes up for the case that if your boring bar is springing away from your part a little bit, flexing, or if your part's flexing away from the boring bar. So spring passes really make your work more accurate. Here's another tip for you. If you're just hogging out material, roughing out your size, you can pull the boring bar out with the spindle turning. But when you get down to close tolerance, you get down close to your final size, when you pull the boring bar out of the hole, you want to turn the spindle off first. That way it doesn't drag back across the bore and eat a bunch of material out on the way back out. And now if you turn the spindle off and pull the boring bar out, it'll leave a tiny little scribe line where the tip of the insert or cutting tool drags inside the part. But if you're only taking 1 thousandths or 2 thousandths finish cuts, that line is almost not even noticeable. Now before I cut this off, I want you guys to notice that I turned down a second shoulder there on the right hand side of the part. That little shoulder is 2 thousandths smaller in diameter than the rest of the part. The main part of the part is press fit for the bore that's going to be in the spindles, and that little shoulder is 2 thousandths smaller than the press fit. That lets your bushing start down in the hole and start straight. In other words, that 2 thousandth step will just slip down in the bore of the spindle, and that'll get the bushing lined up perfectly straight, and then I'll press the rest of it in. Now this is called a part-off tool or a cut-off tool, and if you notice when I sharpened it earlier, I also ground about 5 degrees of lead on the front of the tool. If you'll notice, the right-hand side of the tool touches the part before the left-hand side. The purpose of that is when it gets all the way in and just about to cut the part off, it will cut off first on the part side, and that will eliminate a lot of burr on the part itself. And then it'll face on in and cut off the stock side. Now also, before I cut the part completely off, I take my file and put a little 45-degree chamfer on the back side of the part, because that's hard to do once you've already cut the part off. Right before the part cuts off, I'm going to stick this pencil in it. The purpose of that is to catch the part when it does cut off. That keeps it from going flying across the room or beating up against the machine bed. That just keeps it from getting messed up. Now, it's probably about this time in the video that you're saying, Puddin' Creek, that sure was a lot of work to make a bronze bushing. Don't you know that you can order bronze bushings like that online for almost no money? Well, yes, I do. But you have to be careful. A lot of times those bronze bushings online are made out of sintered bronze. Let me tell you what I mean. Now this is a sintered bronze bushing. This is not made by the process you just saw me make our bushing. There was no lathe involved, no bar stock, no General Chow's bandsaw. These are made by taking bronze powder and pouring it into a die, and then putting that die under about 45 tons of hydraulic pressure to form a basic shape of the bushing. Then the bushing is removed from the die and put in a centering oven and brought down to the melting point of bronze, and it's kind of all melted together. But what it leaves you is this product right here with all these pores in it. Now the pores can be useful for retaining oil. That's kind of the purpose of them. And also they can be delivered to you pre-oiled or pre-lubricated. And the way they do that is they put the bushing, after it comes out of the centering oven, they put it in a vacuum chamber. The vacuum chamber sucks all of the air out of those pores, and it also sucks the lubricant into the pores. And that can be oil or graphite or whatever lubricant they want. And that way when you order the bushing, it comes right to your door pre-lubricated and ready to go. Now you're probably saying, Puddin' Creek, that sounds like an amazing bushing. How come you don't want to use those on the kingpins for the bad coupe? Well, this is the reason right here. You see these sintered or powdered bronze bushings? They're almost as strong as a cornflake. I'm afraid if we put these in the front end of the bad coupe and the little woman and I were tooling down the road headed to a car show, I'm afraid one of them might break, and me and the little woman and the bad coupe, we might all end up in a ravine. Now I intentionally drilled my grease clearance hole a little bit bigger than the factory ones because I figure it doesn't really matter how big it is, and if it is a little bigger, it makes it easier for me to line it up when I'm pressing it into the spindle. Here's the next step. We got to cut these grease valleys in, and obviously the factory ones were done with some kind of a machine, but I don't have that kind of a machine, so I'll have to cut it in by hand. Now, I have done this many times before, but I've never done it with a bronze bushing or bearing that's this small. Usually when I'm doing something like this in industry, it would have been like a 2-inch diameter bronze bushing or something like that. Nothing as small as this. Now, what I had in mind to do this job was something like these right here. These are old American-made burrs from who knows when. Looks like the 1950s, and I've got several packs of them. That's what I was thinking of, but those are way too small for the job. I'm going to need something bigger that will reach back in that bore, but not so big that I can't get in there and see to work. I think this Dremel tool right here will probably be the hot ticket. We'll give it a try anyway. I took a blue Sharpie and gave myself some guidelines to grind to. Now, I'm pretty sure this is going to turn out as rough as a night in jail, but the good news is it won't be seen in the final assembly of the car. So only me and all 62,000 of you will know how rough it really is. Well, it did turn out pretty rough, but it'll serve the purpose of letting the grease get all the way around the kingpin. I've got 3 more to do, so maybe by the time I get to the 4th one, I'll have it mastered. We'll see. All right, let's get this baby pressed into the spindle. Now, right here is where that little shoulder is going to come into play. If everything works right, that little shoulder should slip right down in the bore by hand, and that will allow me to line it up perfectly straight before I start pressing on it. That way we have no chance of pressing it in crooked. Also, I got to line this grease clearance hole up with the grease fitting hole. I'm going to put a flat washer in between that deep well socket and the new bushing, just because I don't want to take any chance on that deep well socket kind of flaring out the end of my bushing. I want it to be pushing against something totally flat. Now, if everything goes as planned here, I should feel some resistance as it's pushed in, but it shouldn't be rolling up material on the edges of the bushing. It should press in nice and clean, and I do. I feel some resistance. It feels just about like it should. Well, honey hush, that worked just like it's supposed to. My grease fitting hole lined up, everything went in nice and straight, no bronze shaved off the outside diameter. Let's see if the kingpin will fit. I don't expect it will. I expect it will be closed up a couple of thousandths. Yeah, the kingpin don't go in now, but that's totally what we figured on. We'll just have to ream a thousandth or two out of it. Let's take our test pin here and see how much it closed up. Let's see if the 821 will go in there. No, it starts, but it won't quite go in. So it's probably about 820 or something. Yeah, the 819 just falls in, so it's closed up a couple of thousandths. That's no big deal, though. That'll make it real easy to ream, and no chance of it coming out crooked. It'll be nice and straight because it's only scraping out a couple of thousandths. Well, I got General Chow busy sawing up the rest of the kingpin bushing blanks. And in the meantime, I checked on our hairpins that was soaking in the evapor rust, and sure enough, they soaked all day, and 99% of the rust is gone. What little bit of rust is left, the quick blow is going to take off. So I went ahead and pulled them and dried them off, and Let's shine them up and see what we got. Well, good googly moogly, that old 1970s chrome sure does shine up shiny. Well, friends and neighbors, that's our show for this week. We sure appreciate you guys coming back every Monday to hang out with us. Now give us a little feedback on what you think about the show. Leave us a comment and tell us what your favorite thing is about the show, and tell us what your least favorite thing is about the show. Now, if you want to get some Puddin' Creek merch, maybe a Puddin' Creek t-shirt or a Puddin' Creek coffee mug, or maybe a Puddin' Creek trucker hat for your mamaw, just head on over to PuddinCreek.com. And as always, don't forget to subscribe if you haven't already.